Hello, everyone, and thank you for your interest in this work. Over the past few years, we have constantly heard of accelerated development in quantum computing, built atop many decades of research in various sciences. So today we have functioning quantum computers capable of attempting real-world problems and even have demonstrations of quantum supremacy over classical compute, albeit under several constraints. So this is great. So hopefully in the near future, high fidelity quantum machines will become commonplace and quantum computing can become part and parcel of all computing research and development. But today, most of us across the world access quantum devices over the cloud. Further, these machines have low fidelity and are of small sizes, and the best and largest of them are tough to access most of the time due to growing demand for research and development. At the same time, not all applications require the best machines, but we might not have enough knowledge or information to make optimal choices. So this paper is a step towards understanding quantum resources in the cloud and the jobs that are run on these machines. So I'm Gokul Ravi, a postdoc at the University of Chicago, and my collaborators are Kate Smith and Professor Fred Chong from Chicago and Pranav Gokhale from Super.tech. So this work is pursued as a part of EPIC, which is an NSF expedition in computing. So first, a summary before getting into the details. So quantum machines in the cloud are diverse and user demands are constantly growing. This leads to two outcomes. One, users have limited knowledge on as to which machines are the best for their use case. And second, queuing times in the cloud, especially to the best machines, are extremely long. Thus, efficient management of cloud resources is critical. And the first step towards this management is characterizing and understanding the job and machine characteristics. So this works a 2-year analysis of quantum jobs executed across our research group on the IBM Quantum Cloud. The studies performed over 20 machines running 6,000 jobs, which have comprised of over 600,000 circuits, and in all have resulted in a total of over 10 billion machine executions. So based on our analysis, we obtained some insights and recommendations targeting machine diversity, resource management, queuing times, execution times, verification, and compilation. So finally, analysis such as this work are meant to be utilized for efficient optimization and improvements. So in this spirit, we have proposed an intelligent resource manager based on these studies, which appeared at QC 2021 very recently. And this enables wait times to be reduced in the cloud by over 3x and improves fidelity by over 40%. So now a brief background on quantum computing and cloud execution. So quantum computing has the ability to provide considerable benefit across a spectrum of applications in domains such as cryptography, chemistry, optimization, and machine learning. So today we are in the era of the noisy intermediate scale quantum computing, in which quantum machines are under 100 qubits and suffer from multiple forms of error. So error rates are on the decrease, but will remain significant in the near future. And devices with over 100 qubits and even close to 1,000 are on the horizon. So the future of quantum computing looks promising, and therefore the popularity and demand is constantly growing. So since quantum computing is still at a nascent state and quantum computers are a rare and expensive resource, they are mostly accessible only via the quantum clouds of various vendors. And similar to the classical computing in the cloud, efficient management of resources is critical. Unlike the classical cloud, though, on one hand, quantum execution fidelity is significantly affected by machine characteristics. And on the other hand, NISQ era circuits are of low complexity, and thus execution and fidelity trends are fairly predictable if specific features of the machines and jobs are identified and analyzed. So thus, understanding the quantum jobs and machines is critical for the quantum cloud. So now I'll give a brief overview of quantum computing in the cloud. So this figure shows access to the quantum cloud, which is modeled on accessing the IBM cloud. So users create a batch of circuits to execute as a job, and all the circuits within this batch are executed back to back on the quantum machine. So the user selects a machine to execute on and compiles all the circuits in the job for this target machine. The job is then sent to the queue for that machine. It waits in the queue depending on how many jobs are in that queue, and then Once it goes through the queue, it's executed on the machine and then returns to the user. So as I mentioned earlier, understanding the characteristics of quantum jobs and machines are critical to the cloud. So on that note, we first look at machine characteristics in terms of size, topology, and error rates. So here's a snapshot of quantum machines available on IBM's Quantum Cloud. Observe that there's a lot of heterogeneity among these machines, even at this sort of high-level metric of just the number of qubits. The number of qubits ranges from 1 to 5 on really small machines, is around 20 in the medium-sized machines, and as high as 66 on the largest, 65 on the largest machine available. So in the near future, we are hopeful for machines of even greater than 100 qubits, but this sort of diversity in sizes is expected to continue. So clearly, the machine needs to be large enough for a user to execute their application. But which machine do they choose? Do they just go for the best size fit or the largest, or is there a more optimal machine for the task? So going a step beyond just the number of qubits is observing the topology of these machines. So here we see topologies for 7 qubit, 16, 27, and 65 qubit machines. And what stands out is the limited connectivity in these devices, which is a characteristic of superconducting quantum computers. So limitations in connectivity often results in increased circuit depth when applications are mapped to these devices. This usually means that some fidelity expectations you might have for a machine and application are not directly inferable. They are heavily dependent on how the application actually gets mapped onto the device. So next we look at error diversity across these machines, specifically looking at 2-qubit gate C0 errors, which is a major source of error. So the figure on over here shows on the y-axis error and machines on the x-axis, and each set of 3 bars represents a single machine, and the green lines are the max error, orange is minimum, and blue is the average. The machines are sorted by sizes from with largest to the right. So as I mentioned earlier, if connectivity is restricted due to topology or due to other constraints, like avoiding bad qubits, then the resulting circuit might incur a high number of swap operations, which suffers a lot of C0s. So if you observe the average error here, it is evident that they vary pretty widely across the machines. Further, there is considerable difference between the maximum and minimum from the average on all these machines. Thus, there is a lot of diversity in these machines in terms of error rates. And also observe here that these errors are not necessarily correlate with the device size. So selecting a larger machine doesn't always mean better fidelity. So comprehending error rates becomes even more challenging due to the fact that these error rates change over time. So machines are recalibrated on a regular basis, and error rates can be very different in different calibration cycles. So this figure shows C0 error measurements on a particular pair of qubits on a 5-qubit ROM device. The data is collected over a nearly 3-month period. So you can observe that the C0 error can vary widely from day to day, which is especially evident in this line in green. So further, some C0 pairs become better or worse than others over time, which sort of highlights that it's tough to track the errors or make predictions of the errors in these machines. There are also other sources of error apart from the 2-qubit C0 errors, such as single qubit error, crosstalk between qubits, and qubit decoherence, all of which result in qubits losing their state. Thus, it's clear that machine characteristics are pretty challenging to comprehend and heavily influence the best machine for a use case. So having established that machines can be pretty diverse, users often select machines for their jobs based on some heuristics, but these are often simple and suboptimal. And this often leads to some unfavorable job trends in the cloud. So first we look at queuing times in the cloud. So this figure shows queuing times experienced by our jobs on the IBM cloud over the 2-year period. The green lines correspond to times of 1 minute and 2 hours. So from the figure, it can be inferred that the median queuing time is around 1 hour, while more than 25% of the circuits are queued for 2 hours or more. and further 5% of the jobs are queued for even more than a day. So it's clear that the wait times are pretty significant and will continue to grow as the interest in quantum computing and the demand for its access grows drastically. So next we dive into some machine trends. So this figure shows the average pending jobs across many IBM machines, averaged over 2 separate weeks in March and May of this year. The publicly accessible machine is circled in purple. So clearly the average pending jobs vary from just tens of jobs to multiple thousands across machines, and these trends are not uniform. The publicly accessible machines, for example, tend to have a higher demand, and this is expected. But even among the private machines as a cluster and the public machine cluster, this load is not balanced. So in this figure, the machines are grouped by the blue lines based on their sizes. And you can see that even within a group, the pending jobs across machines vary widely. For example, all the machines in the second block from the left are 5-qubit machines. And some of these have over 1,000 jobs queued, while some have very few. And also, these distributions are not stable over time. And this can be influenced by some heavily targeted experiments on some particular devices, which is why the trend from March is pretty different from the trend in May. And further, so new policies for extended machine reservations are being introduced, which are critical for long-running experiments like variational algorithms, and these can skew trends even further. Thus, clearly, any opportunity for load balancing while being cognizant of machine characteristics is very important for the cloud. Next, we look at machine utilization, which is the fraction of machine qubits that were used by a circuit. So even though a 65-qubit machine like this IBM Manhattan can technically run a 65-qubit application, this utilization is considerably lower due to the limited connectivity which we discussed earlier. And so low utilization on very large machines is expected, but you can also see that even on the smaller and the medium-sized machine, the utilization is pretty poor. For example, if you look at the first line from the left, which is a 16-qubit machine, you can see that the utilization is under 0.5 most of the time, which means that only like 5-6 qubit circuits are being executed on the 16-qubit machine. This is often because users tend to choose like one single machine and then use it across a lot of their circuits, or might just use it since it's a larger machine and hope that it will provide higher fidelity. Or at some point they might have found it to be lightly loaded and continued to use it for a period of time. Note that all of these heuristics, as I are just how I describe them, and they are suboptimal for sort of both from a user perspective as well as from the perspective of maximizing the efficiency from the cloud, both in terms of throughput as well as in terms of fidelity. So it's also interesting to point out here that these increased wait times due to waiting for a long time in a particular machine's queue is not just a latency penalty for a user. It's because, as I mentioned earlier, these machines are recalibrated at some intervals of time. For example, IBM machines are calibrated once a day. So the change in noise characteristics from one calibration cycle to another means that so the compilations which use noise data from an old calibration would have created a mapping which is optimal for the previous calibration, but is not optimal for the new profile of the system. So on the left in the pie chart, you can see that over 20% of our jobs were compiled for one cycle, but then they crossed over and were executed on a subsequent cycle. And while this is not always suboptimal, it can lead to cases like the one shown on the right. So on the right, the top figure shows an old compile and the bottom shows a new compile. And these compilations are done for like subsequent calibration cycles. So clearly the mappings and circuits are very different, and using the stale compilation from the top during a new calibration cycle can lead to suboptimal execution. And this can be particularly detrimental because researchers are often targeting experiments which are at the brink of reasonable fidelity. So we would want every layer of optimization to be perfect. Okay, so thus, as we just saw through some of these trends, load is imbalanced and queuing times are often very long. And they are influenced by suboptimal machine to application mappings. Okay. Apart from these, the paper features many other observations as well, which I will sort of quickly highlight. So one, we discussed the prevalence of errors, sort of program errors, which result in lowering of system throughput. So quantum program verification is still at a pretty early stage and requires considerable development since application complexity is on the increase and there is more possibility of errors occurring, which can be even more detrimental to a cloud which is already under significant demand. So second, the paper reinforces the fact that wait times can be very detrimental by discussing the queuing to execution time ratios, which are often in the range of 10 to 100x and sometimes even 1000x. And this is a significant impact on research and development if you have to wait 1000x the time for like for 1x time of execution. Three, we discuss compilation times. So in the past few years, we have seen a lot of work towards in the quantum software stack for creating better compilations to improve fidelity and so on. But a lot of these optimizations are not very scalable. So we show that, for example, as we move from a 64 qubit circuit to a 1000 qubit circuit, the runtime for some of these compilation passes goes into many hours. And this is bad because compilation is closely tied to the execution and is usually performed just before launching or running a circuit. And this would add to even greater overheads. Fourth, so I discussed the diversity in machine topology earlier. So in the paper, we also quantify this in terms of bisection bandwidth, which is a concept that audience from like network background would be familiar with. Okay, so as I mentioned earlier, the goals of characterization papers are to use some of these characterization data to build some optimizations. And as I had mentioned, we have proposed this quantum cloud resource manager, which consists of multiple components. So one of this component is this ability to predict queuing times using by predicting runtimes. So in the figure here, the y-axis shows the correlation between predicted and actual runtimes. Higher is better. And you can see that the correlation, there is the predicted correlation. The correlation of the predicted runtime with the actual runtime is higher than 0.95 on all but two machines. The ones with poor correlation are at least partially a consequence of extremely low runtimes. So next, the correlation is broken down into multiple correlation components, which are shown in the legend. So they are batch size, which is the number of circuits in a job, the number of shorts in a circuit, the width and depth of the circuit, as well as some other less significant features. So the main contributor to this runtime prediction is clearly the batch size. And what this implies is that irrespective of the circuits involved, the number of circuits in a batch is loosely proportional to the runtime. A second contributor is the number of shots in the circuit, which is influential when the batch size is low. And other factors like depth, width, and memory slots have very limited influence. So this trend is not unexpected because in the NISQ era, algorithmic depth and complexity of circuits are pretty limited. And therefore, the overheads associated with the execution of a circuit is more influential than the characteristics of the circuit itself. And this trend is expected to persist in the near term. Next, we show an example of this runtime prediction at work. So the figure here shows the actual versus predicted runtimes for jobs run on the IBM Manhattan machine for over 100 jobs. So while machine and job characteristics can vary widely across these jobs, the application runtimes remain very accurately predictable. And as runtimes are predicted over all the jobs in a queue, and they can be accumulated to obtain a prediction for queuing times, which can then be used towards the resource manager. Next, we discuss the ability to provide a correlation between fidelity and job characteristics. So our correlator uses 4 features of a circuit which is compiled to a particular quantum machine. These features are circuit depth, average C0 error, the average C0 error in the circuit and average in the critical path, and readout errors. And while we observed a good set of features, there is significant room to add more, reduce redundant features, and so on. So these features are put together into a model, and they are modeled as a product. The correlator's output is a product of linear terms, and the coefficients are tuned using a curve fitting approach. And the figure here shows correlation between the actual application fidelity and the tuned model, as well as with each feature. So a coefficient greater than 0.8 is considered very good, while coefficients in the 0.6 to 0.8 range are considered useful. So while 3 of the 4 features here provide useful correlation, the combined produces very high correlation on the device models. We then also test this on a real machine, which is shown in orange. So while the correlation falls a little bit, it is still in the useful range. And so it is possible to improve this correlation by identifying more features to tune on, and also more diligently characterizing the characteristics of the machine itself. And using these features, the proposal was to automate the job and machine management process. And we designed a job and resource manager that can select the best machine for a job based on multiple constraints and QoS requirements. So I'll just briefly go through the working details of the job and resource manager. So first, a representative quantum circuit is selected and compiled for all suitable machines. Post-compilation features of the circuit are passed to this fidelity correlator, which I just described. The correlator returns a correlation metric, which is a fidelity estimation across different machines. In parallel to this, the queuing information, job size, and number of shots are used to predict wait times in each machines. And other constraints like QoS requirements and calibration schedules are taken into account. So all this information is put together and is pushed through a utility function which returns an optimal machine. And this machine will be used for all the circuits in this job. And so this selection of a machine through this process is better than sort of naively selecting a machine, because it optimizes for both fidelity as well as balances in terms of balance of the load across different machines. Finally, to conclude, I will discuss the scope of the study, contrast against the classical cloud, and we'll discuss some insights and recommendations. So our study has focused on data collected across the IBM's fleet for over a 2-year period. The queuing data we obtained is generally applicable to all users on IBM quantum systems, because and further, the increasing demand for machines is not limited to IBM machines, thanks to different machines accessible across vendors. As I discussed earlier, the execution data is less closely tied to the specifics of the quantum circuit and more to the size of the jobs and number of shots and so on. And so it is also generally applicable to across all users. The general impact of calibration, noise characteristics, device connectivity, and so forth on circuits are not specifically restricted to the circuits itself and are generally applicable. Further, the IBM quantum machines are superconducting devices, and these machines in general are limited in connectivity, are noisy, and require calibrations. And hence, our results and recommendations for IBM quantum machines should be generally applicable across other superconducting devices as well. Trapped ion machines, for example, achieve better connectivity and lower error rates, but still require calibration and can benefit from appropriate machine choices. So our insights are broadly applicable over there as well, while we encourage more studies. Now, to contrast against the classical cloud, we note that while verification and incorrect execution are common in classical computing, the challenge in quantum computing is that verification techniques are at a very nascent stage. Quantum compilation is deeply tied to the characteristics of the hardware, and quantum compiled executables cannot be distributed independent of a machine. Choosing the right machine to maximize fidelity is unique to quantum computing, and especially complex given the unique interactions of quantum computation that the environment executes in. While reducing queuing times is well researched in the classical domain, they're even more critical in the quantum domain because of the drift in quantum characteristics. And finally, execution times in quantum machines are highly predictable compared to classical computing because overheads dominate the execution times. Finally, some insights and recommendations. As circuit complexity increases, so will the potential for mistakes and incorrect executions. So debugging and verification strategies are a must for maximizing useful system utilization. Compilation times are on the increase, and so there's a need to build more scalable compilation strategies. Machine characteristics vary widely across machines. And so using some particular characteristics like 2-qubit gate errors and so on to predict or get some insight on machine fidelity is useful. And as we just saw discussed over here, demand for resources is constantly on the increase and machines are very diverse, so resource management is a must. Load imbalance leads to significantly varying queuing times, which not only reduces system throughput, but also impacts application fidelity. So queuing time will become more challenging to predict in the future, so more research on this is critical. And at the present moment, execution times are more predictable, but as complexity of algorithms or circuits increases, this will become more challenging. So utilizing more features to predict execution times is worth studying as well. Yeah. Thank you.